So it's a great pleasure to welcome Lee Kennard of Syracuse University, who will speak on systems of graphs and torus representations.
Okay, thank you, Carolyn, and thank you, Emilio and Ramiro, for getting this thing started. And I saw Fernando's helping with organization too, so thanks to you too. I want to start with 2 slides on Riemannian geometry. This is our main focus. This is where our applications are. But what I'm going to spend the bulk of the talk on after that is talking about torus representations. It's completely elementary, and it has nothing to do with curvature, but potentially they have applications, these ideas and techniques to other areas of differential geometry. So stay tuned, even if you're not interested in positive sectional curvature. This is where our applications are, though, so I'll start with this. Dealing with compact manifolds, and I'm going to restrict to even dimensions for simplicity. I am assuming there's a Riemannian metric. I don't need to give it a name because most of our work is really more topological and combinatorial, so we don't really work with the metric, so I'm not going to give it a name, but it has positive sectional curvature and it has torus symmetry. Prototypical examples are the compact rank 1 symmetric spaces, the spheres and projective spaces, and the Cayley plane. And our first major theorem, I spoke about this 3 years ago in this seminar, so I'm assuming all of you went back and watched that YouTube video. If not, I'll very quickly remind you the theorem I was singing and dancing about was part 1 of this theorem. This says that if you have a 5-dimensional torus action, then you can prove that the Euler characteristic is positive. So remember, even dimensional manifold, so at least that's possible. This is conjecturally true. Hopf conjectured this in the 1930s without any symmetry assumption, but this is the best evidence. At the time, this was the best evidence in the presence of symmetry for this. There were previous results with torus symmetry, but the rank of the torus was bounded below by a constant that depended on the dimension of the manifold. Here, it doesn't. So that was what was really exciting about this result. On the same paper, we proved a more global topological result. We computed the rational cohomology ring. So this is my Beamer notation for rational cohomology ring being the same. All right. So we compute the rational cohomology ring, and the torus symmetry is just a little bit bigger, but we have this additional assumption in blue, which is that the odd Betti numbers vanish. This should hold conjecturally by combining with the conjecture of Bott, Grove, and Halperin. It's a conjecture, so we need to make this assumption. I should mention that a student of Burkhard, Jan Nienhaus, has refined one of the tools that go into this. And I'll just briefly say that if these same exact statements are true, but you only need to assume a T4 action in this case and a T6 action in this case. I think this is pretty exciting because if you try to go further and relax to a T3 or a T5, it might be true, but if you relax one step further than that, it's false. So specifically for the second statement, if you relax a T7 all the way to a T4, it's false. The Wallach manifold is an example, the Cayley plane as well. But even the first result, it might still be true, but the proof method that we use fails because if you can look at a T2 action, T2 sub action on the Wallach manifold at dimension 24 and get fixed points that aren't standard. So like our method of proof breaks down. So I think of Jan's result as being either optimal already and we don't know it, or at worst, it's off by 1 from being optimal. All right, some newer results. The first of these has a very similar feel. You have a torus action where the rank doesn't depend on the dimension of the manifold. And the key thing is we're replacing this strong topological assumption on the Betti numbers by a geometric assumption on the torus action. I'm going to talk the rest of the talk about this blue condition CIG. So just stick with me for a minute. It's a more geometric assumption. And then the conclusion is the same. that the rational cohomology ring agrees with one of these standard models. That's already on the archive, this second preprint. And then the second result here is going in a different direction. So here, instead of assuming something topological or assuming something geometric, we want to make no additional assumptions. We just want to dial up the symmetry until we can get a more global computation. What I mean by this is like this result is nice, but it's only an estimate on the Euler characteristic. What do we need to assume to get a computation? So here, the Betti numbers give you more than that. They give you the whole cohomology. Here, this geometric assumption on the torus action, again, gives you the whole cohomology. Here, if you want to assume nothing except crank up the symmetry, then it's a little bit better than this. There's a constant, but it doesn't fit on the slide. So here's pretty much the result. So if D is a logarithm of n, then we can compute the Euler characteristic. And the answer is that it agrees with one of these models in orange. All right. So dimension 16, for example, if you plug that in, you get symmetry rank 4. Cayley plane has symmetry rank 4, so that fits on the list. By the way, dimensions 16 and lower were already computed. Some of this in joint work of myself and Manuel Aman. So this is new in dimensions bigger than 16. In addition to that, though, we get kind of half of a computation. So we don't compute the cohomology ring, but we prove an inclusion. It contains this, contains a cohomology of this model. And what that means, for example, in the CP case is that there's an element in degree 2, cohomology. And when you square and take powers of it, all of those powers are non-trivial. So there's an embedding of the cohomology of CP inside the cohomology of the manifold. Just to throw it out there, what's missing really for equality is some additional assumption. And it's tempting to think maybe with logarithmic symmetry, one could, by other means, prove that the odd Betti numbers vanish. That would be pretty exciting. That would turn theorem 2 into a computation of the cohomology. But I don't know how to do that. So we're gonna stick with these for now. All right, so I want to discuss some of the existing tools first. A major one is the connectedness lemma due to Wilking in 2003. This, qualitatively speaking, this relates to homotopy groups.
Lee, can I ask a question?
Sure.
How are you?
Hi.
Can you go back one slide? So in that model M hat is a sphere, it doesn't say that much. It's just the cohomology of the sphere lies in cohomology of M. That doesn't say anything.
That's right. Doesn't say anything. Yeah, for the sphere case, it's just that the Euler characteristic is equal to 2. That's all.
So if chi of M is 2, he can't say anything. Chi
That's
of
right.
M is 2, he can't say anything.
Right.
Oh, okay. Thanks.
Yeah, yeah, somehow that's the case when you would think maybe that would be the case when you can say a little bit more, but it's kind of the opposite. Yeah.
Okay.
Yeah, but I think I want to emphasize that this statement already is saying that the Euler characteristic is not just positive, but it's one of those 4 possible, really basically 3 possible values. Yeah.
That's of course a strong statement. I understand.
Yeah. Okay. So the connectedness lemma I mentioned relates to homotopy groups of a positively curved manifold to those of its totally geodesic submanifolds. This is important in the presence of symmetry and positive curvature because it's well known that you get fixed points and that fixed points of isometric actions are totally geodesic. And so the quantitative statement involves the codimensions to tell you how many homotopy groups you get. I'm not getting into those details, but this has had lots of applications in this context. Another lemma due to Burkhard's paper is that if you have one of these totally geodesic submanifolds and the inclusion map gives you isomorphisms on homotopy groups, if you turn this into statements about homology and cohomology, and you combine with Poincare duality, you get a notion of periodic cohomology. you get, I don't want to define what this means, but it means in particular that the Betti numbers are periodic. That's hopefully already convincing that that's a strong condition. All right, and then something in a paper of mine from 2013, it's called the four-periodicity theorem. This says if you have periodic homology with integer coefficients, as you get from Burkhard's work, then you get finer periods using different coefficient groups, and specifically using Steenrod squares and Steenrod powers. You can refine the period. You can prove there's a smaller period. And then if you move to rational coefficients, that's where the best statement is. You get a fixed period of 4. You get 4 periodic Betti numbers, and more specifically, 4 periodic rational cohomology. So I'm not going to tell you exactly what that is. I want to tell you what it means. So there's additional work in my first paper with Wiemeler and Wilking, where we show that in the context, in the settings where this occurs, so we have torus actions, positive curvature, compact manifolds, okay, fixed point sets of circles, in some specific instances where you get 4 periodic rational cohomology, you can prove additional statements. One of them is that the third Betti number vanishes. This is a non-trivial computation. And second of all, that you don't get things like sphere times HP. So for example, S2 times HP has 4 periodic rational cohomology. We don't expect that to be on the list of positively curved manifolds. So the lemma is, I call it the S times HP lemma. It's showing that it's not that. So the short story is that 4 periodic rational cohomology implies that the cohomology ring is one of these 3 model spaces. In the settings, these lemmas have extra conditions, but in the settings where these occur, you put all of this together and you get these sorts of statements that the rational cohomology is standard. All right. And what this means is that all of the work, a big chunk of the work is proving that you get enough fixed point sets and good enough intersections of fixed point sets to feed into the connectedness and periodicity results. So what I want to spend the rest of this talk on is talking about what we prove for torus actions. And specifically for constant curvature, we have that'd be easy. For positive curvature, we have fixed points. And so we look at the isotropy representations. And so really these turn into just statements about torus representations. The first one is the S1 splitting theorem. This proves the existence of transversely intersecting fixed point sets. I'll get to that in the next slide. And then the second type of result has to do with proving bounds on the codimensions of fixed point sets. So this involves a few different things. So with this blue condition, this means connected isotropy groups. This involves a classification of those representations, which I'll discuss later. And using that classification, the problems on codimensions of fixed point sets turns into a problem about graph systoles. So these are like lengths of shortest curves, lengths of shortest cycles in graphs. And fortunately or unfortunately, we couldn't find the estimates we needed, so we did a little graph theory to prove some new results there. And that tells us about fixed point sets of torus actions. In the general case, so in this where the D is a logarithm of n, we go back to thinking about involutions. This idea was introduced in Wilking's paper. So you think about this as an error correcting code, and believe it or not, we're still learning things about these in this dimension range for the representations. All right, so let me discuss this splitting theorem. I'll state it, I think, as simply as I can. So you have a torus representation. It's a faithful representation, and this might not split. That's easy to write down examples. However, you can pass to a one-dimensional subgroup and look at its fixed point set. Okay, so H is a circle, maybe, but it's usually a disconnected one-dimensional subgroup. You can cut down the dimension of the vector space enough so that the induced action splits in this sense. So the torus, of course, splits abstractly, but you can split it in such a way that the Z component only acts here, and then the other components only act here. Right? And in particular, you can see immediately, if you look at the fixed point sets of the circle and the torus, they intersect transversely. That's for the geometric application. So here's an example. This is a T3 representation. I just wrote some representations down. One thing you can do is first look at this Z2 subgroup, look at its fixed point set. So the ABC coordinates all act non-trivially, and the ABC does as well. And so you're left with these purple coordinates for the fixed point set. All right. Then you can increase the subgroup to a one-dimensional subgroup by taking the Z3 factor or the C factor, and then that cuts away the components that have a C in them. And so the fixed point set of that one-dimensional subgroup has these three parts left. And you can work out the isomorphism from T3 mod H to T2. You know that it's abstractly 2, but maybe it takes a minute to write it down. And the induced representation, this should be a U3. Looks like this. And so you can see the ZZ leftover part with the other coordinates. The reason I did this example, and I did it specifically in this way, is because it's a general thing that you can use finite subgroups, and specifically finite isotropy groups, to cut down your problem. And specifically, you can use them to cut it all the way down to the case where all isotropy groups are connected. So the idea here is that you take a finite isotropy group and one that's maximal with respect to inclusion. You look at its fixed point set. Now the induced action of the torus is now on a smaller dimensional vector space, but this torus is a torus of the same size as the original one. So by induction, you can, what am I saying? Not by induction. What I'm saying is that, sorry, I'm proving something different. Because this was a maximal finite isotropy group, you can prove that this induced action has connected isotropy groups. Okay, so now you still have to prove the theorem in that special case, but this was how we proved the splitting theorem, was by restricting to this special case. And what's nice about this is that this is a very restrictive condition, this connected isotropy groups. I'm going to talk about it now. So what it means is that, maybe you can guess already. So it means that for any vector in your vector space, if you take the isotropy subgroup, the subgroup of elements that fix it, that should be a row of G acting on V. The assumption is that that's trivial or a circle or a T2. It's a connected subgroup of the torus. I'm going to tell you about these, but first I want to motivate this a little bit. This is a generalization of the notion of semi-free circle actions. So those are pretty nice actions. You still have nice geometry of the orbit space and so on, but they're richer. It's a richer class than just the free one. So this is one generalization of that. These sorts of representations always arise. So for a general torus representation, you can do what I did on the previous slide, and you can get a torus representation with connected isotropy groups. So somehow they're always present. And maybe most compelling is that it might help you prove theorems. So I mentioned that the first proof of the splitting theorem was done in this way, reduced to this case, and then you study the result you're trying to prove in this special case. And then it might help you prove the result in general. So let me get into a little more detail. Here's a T2 representation, pretty mild representation, but this has multiple disconnected isotropy groups. So this is one that does not have CIG. You can see the Z1 to the third power is going to give you an order 3 finite isotropy group. What I've done here, I've just looked at E3, so actually it's a disconnected isotropy group. This one, if you look at the components E4 and E5, if you require both of those to be identity, you get a Z2 subgroup. So those are examples of disconnected isotropy groups. And it's a statement, it's a straightforward exercise with the slice theorem that if you have a disconnected isotropy group, you get a finite non-trivial isotropy group. This was proved in our paper. It is also, we found it in Fang and Rong's paper from 2005. So disconnected and finite isotropy groups, kind of the same condition. What I want to point out here, though, is that this condition of having a disconnected isotropy group can be detected by looking at the weight matrix and specifically determinants of submatrices. So what I've done here is I've taken the exponents like z1 to the 1, z2 to the -1, and put those as column vectors. These are the weights of the representation. And you can see this red submatrix here corresponds to these two directions, these two irreducible subrepresentations. And that submatrix has determinant 2, -2. It's 2, plus or minus 2. Either one would give you, this would detect the fact that there's a rank 2 or an order 2 finite isotropy group. This one over here with the 3, if you put it together with this one, for example, you get determinant -3. So that's detecting the fact that there's an isotropy group of size 3. So this condition, we knew about this condition for a long time. We didn't know what it meant. It wasn't until a very lucky Google search that we figured out what this meant. We learned that these sorts of matrices have a name. They're called totally unimodular. So these are matrices. So think of the weight matrix of a representation. It's a bunch of integers. And this condition of totally unimodular is that if you take any k rows and any k columns and take that submatrix, that the determinant is plus or minus 1 or 0, plus or minus 1 or 0. Okay, that's just a name. But the fact that these had a name meant that we knew what to Google. All right, so we Googled those and we learned that they're really important actually in combinatorics and applied mathematics, and they've been studied a lot. What we learned eventually was that they are in one-to-one correspondence up to a notion of equivalence with these strange and abstract combinatorial objects called regular matroids. Okay, so there's something else to Google. We threw that into the search bar and we learned that, we were very lucky. We learned that these were classified in 1980 by Seymour. This is not Seymour's most famous theorem in graph theory and combinatorics, but this is a big one. It states that a regular matroid can be built from so-called graphic matroids and co-graphic matroids plus one sporadic matroid by way of a few operations that he calls k-sums. Okay, we read this, we were excited, we had no idea what any of these words meant. So it took us a while to interpret this. But what we did basically was translate this result from matroid theoretic language into what we considered elementary language of representations. And it gives us a classification. Just by translating Seymour's result, we got a classification of torus representations with connected isotropy groups. And something I want to advertise is that we spent some time in this paper just explaining what the representations look like. So we have seen this condition of connected isotropy groups come up in other contexts involving tori, and we think maybe this might be useful to somebody. We explain what the k-sums look like. We explain what graphic and co-graphic representations look like. And the sporadic is just one particular one. So that's straightforward. But we spend a section describing this classification. I want to check my time. Yeah, I've got time for this. So I want to explain quickly here the most important and largest class of these are the so-called co-graphic matroids, which we then call co-graphic representations in that language. So what you do is, and again, this is from Seymour. Seymour says that this is one of the classes of regular matroid, and so anyway, it seems a little unmotivated, but this is what it tells us. So you take a finite graph, and for each edge in that graph, you think about the map, you think about CW, think about the CW chain complex, like you're computing the CW homology. All right, and you think of, so C1 is a direct sum over edges, and you send the edge E to 1 and all the other edges to 0, right? You think of this as a map on the 1 cells. You restrict it to the kernel of the boundary map. And because it's a graph, there's no 2 cells. So the kernel of the boundary map is the same as the first homology group. So you can think of this E star when you restrict as a map from the first homology group to Z. All right. And again, you know, there's no 2 cells. So the first homology group is just that's direct sum of Z, B times, or B is the first Betti number. All right. And then, you know, when you have a map like this from Z, something that's Z to the B to Z, you can think of that as a weight of a torus representation. And what I'm thinking of is, right, it's described by B integers. You take those B integers and you put those as the exponents of Z1, Z2 through ZB. It's the most elementary way to think about it. And so this gives us a torus representation of TB. All right, that was for one edge. Of course, you can take the direct sum over edges, and this gives a representation where the dimension of the representation is the number of edges in the graph. And it's actually a nice little exercise. I wouldn't call it easy, but you can try to prove that this representation always has connected isotropy groups. And again, Seymour's theorem is saying that basically this construction together with a dual construction, together with that one sporadic matroid are the only ones, together with the notion of K-sums. All right, so, sorry, I need to say one more thing. This classification was nice, but I think it is nice, and I hope it finds other uses. But I want to say that we were working on codimensions of fixed point sets, like I said near the beginning. We were proving all sorts of estimates and all sorts of structure results for the representations, but we just couldn't prove what we wanted to prove, an optimal result that we wanted. Finding Seymour's theorem, though, gave us an avenue. So it told us, okay, we should consider the graphic representations, the co-graphic ones, the sporadic one, and then figure out some kind of lemma for the decomposable ones. This gave us an avenue toward solving our problem. And the problem is this. This is the conclusion. And this is, I'm calling this structure result 2. So it's for any representation with connected isotropy groups. You can consider the subgroups and the smallest subgroups that are circles. You look at those fixed point sets. And our goal geometrically was to find big fixed point sets. So this means small codimensions. So we want to find the minimum codimension of fixed point sets. We normalize in this way. So this you can think of as like the percentage of the total dimension that the fixed point set's taking up. And what we proved is that if you take a minimum over all circles and call that invariant C of rho, that's bounded above by a constant that only depends on the rank of the torus. All right, this invariant does not, this bound anyway, does not depend on the dimension of the vector space. All right, geometrically, the dimension of the vector space is like the dimension of the manifold because it's basically the tangent space. So this already is showing you that something about connected isotropy groups gives you dimension independent results. All right, and okay, so actually so far I've not said anything. What's important here is that this constant also goes to 0 as d goes to infinity. Okay, what that means is that if it goes to 0, it eventually crosses beneath any positive number. I think most of our calculus students could argue that. But specifically, it reaches 1/4 at some point. And if you dig into the quantitative version of the connectedness lemma, 1/4 is a critical codimension for proving the results we needed. So this was important to us to know that at some value of d, this constant is beneath 1/4. And for whatever that constant is, for example, we had estimates long ago showing it was, I don't know, 20 or something. So what this means is for tori of rank 20, there's a weak version of the T9 theorem I mentioned before. Instead of T9, it's T20, but again, independent of the dimension. Okay, but now you can see what we were thinking. Okay, 20 didn't mean anything. Well, what was the D where this hit a quarter? And this is what we really used matroid theory for, really used Seymour's classification for. So it turns out that value D equals 9 is precisely the point when this hits a quarter. The smaller values are too big. So C of 8, for example, is 2/7, and that's optimal. So T8, we can't, our method doesn't work for T8. We really need to use a T9. All right, so that was the main geometric result. I want to explain that the extremal cases here, first of all, are the sporadic representation. This is for a T5 representation. I give you the irreducible representations here. You sort of cyclically shift the components, so there's 10 of them total. This has all sorts of beautiful properties. It's actually very symmetric if you think about the 10 points and R10, R5, excuse me. The other, really the extremal case, aside from that one sporadic representation, is the cographic representations that I defined on the last slide. So I want to spend the next slide talking about those. I did something weird. Hold on a minute. Sorry. Hope that doesn't happen again. Okay, so cographic representation. So again, we've got all representations with connected isotropy groups, and we proved that these are in one-to-one correspondence with regular matroids. And by Seymour, there's the different types, and so this is a subset of all regular matroids, the cographic matroids. And I've expressed that these are the problem cases. This is the largest important class. This is where we really need to do this case. This was the hardest case. And whatever representations correspond to those ones are called cographic representations in our paper. So I explained a little bit that these are representations of a torus that come from a graph. All right, and I'm going to denote the Betti number by B. Remember, B was the Betti number. And remember, the irreducible representations correspond to edges in the graph. Each edge gives you one. And if you have, what I didn't mention before was multiplicity. So, of course, you're not really introducing anything new in the sense of representations. You're just repeating things you already have. So there's a few different ways to denote this, but kind of a nice way is to put integer weights on the edges. This is just labeling the multiplicities of the representations. All right, so one easy thing to see is if you add up all of those weights, I call that the total length of the graph. That's the dimension of your representation. That was part of the quantity C of rho that we were computing. Now, what else? This I can't explain in 5 minutes, but if you look at circle subgroups of the torus, these correspond, like a choice of a circle is similar to choosing a cycle in the graph. So a closed curve in the graph. And what's more important, more specifically, when you look at the fixed point set of that circle and measure its codimension, that's counted by the length of that cycle. All right. Now, we want to know the codimension. We want to minimize over circles. Well, that's like measuring lengths of cycles and minimizing over cycles. That's like looking for a shortest cycle. This is called the girth classically, or the weighted girth, if it's a weighted graph like we're dealing with here. If you allow the measure or the weights to vary, then you can think of it as a graph systole, like a systole instead. That's by analogy with the geometric situation where you're looking at closed curves on surfaces and you allow the metric to vary. All right, but you're still trying to prove bounds for the shortest curve. The shortest curve is less than some constant that doesn't depend on the Riemannian metric. So that's where we're getting this name graph systoles. Also, we're not the only ones to call them that. So yeah, again, so this is kind of repeating what I said. So proving an upper bound for this representation invariant, in this case of cographic representations, is equivalent to proving upper bounds for graph systoles, where the graphs are, which graphs? Graphs with Betti number B. All right, so the first theorem I mentioned in the cographic case is equivalent to this theorem. This theorem says that for any weighted graph, the invariant defined in this way, minimize over cycles and take the length of the cycle and normalize it. This is bounded above by a constant. We call it S of B. And again, that S of B goes to 0. And here B is the Betti number. All right. So just to say something obvious, the Betti number doesn't depend on the number of edges. Remember, the number of edges was like the number of representations. So anyway, this only depends on the Betti number. And moreover, we prove optimal bounds for Betti numbers up to 9. And you can see here, you get 1/4. That's that magic critical codimension. And that's S of 9 is the same as the bound for the other theorem. I mentioned that this was the extremal case. Similarly, for Betti number 8, you get this 2/7 number that we saw before. S of 7, if you want to challenge, is 3/10. And I want to just illustrate some other optimal values. These are little homework problems that you can do now. So for S of 4, it's pretty straightforward to prove that the upper bound there is 4/9. And a graph that realizes this, that shows that that's optimal, is the famous graph K33. Like the 3 utilities problem and thinking about planarity as a condition. For S of 5, the value is 3/8. This is realized by a graph that I like a lot. It's called the Mobius ladder. So you think of a ladder as having sides and then rungs. So imagine a ladder that you've put on the ground. So it has sides and then rungs this way. You think of the rungs as edges and each chunk of the sides as edges. And then what you do is you take the 2 ends of the ladder and you wrap them around to connect it. All right, there's 2 ways to do it. One where you wrap around a cylinder and the other where you wrap around a Mobius band. This is the ladder. That's a graph with 8 vertices, 12 edges, and its systole is 3/8, and it's the extreme case. For S of 6, this is another pretty graph. The value is 1/3, and the graph, one of the graphs that realizes this is called the hemidodecahedron. So I can't resist telling you about this. What you do is you take the dodecahedron that has 20 vertices, 30 edges, and 12 sides. Okay. You can think of this as being homeomorphic to S2. All right. And if you look at the action by the antipodal map on S2, it takes vertices to vertices and edges to edges. All right. So the graph, which is given by the vertices and edges of the dodecahedron, is invariant under this free Z2 action. So you can divide by that Z2 action and you get a new graph, a different graph with half as many vertices and half as many edges. And it turns out, what did I say? So this one has 10 vertices, 15 edges. It has girth 5. It's the smallest cubic graph with girth 5. And so it's also called the Peterson graph. It's famous in graph theory. Anyway, it's got systole of 1/3. Okay, there was previous work. So of course, this is seems like an elementary problem on graphs. And so we looked into the literature and we found this paper by Bola, Bosch, and Sesmoretti from 2002. And they proved, they also proved this part about there being a bound that only depends on the Betti number. And they proved specifically it's similar to the prime number function, log B over B. All right, there's some constant there. I think that the constant isn't huge. I want to say it's 4 something. But anyway, they prove an asymptotic bound. In their introduction, okay, so again, that's what they're really interested in. So they state a few small values in their introduction, and they state for the values up to 6. And I mentioned these values up to 6 are significantly easier than the values for 7, 8, and 9. They're very good prominent graph theorists. I think they probably did these ones in their head. But anyway, for these values, they state the optimal values and they agreed with our values. So we were feeling pretty good about what we had done. We emailed them though to say, okay, you did this 20 years ago. Surely someone's used a computer to compute the next 1,000 values or something. We'd like to know if these have been computed before. We did 7, 8, and 9. Here's what we got. We needed it for our geometry problem. They wrote a nice email back. They said, we didn't break our backs computing the next few values, and we don't know anyone else that did. In fact, we'd be amazed. He said, amazed if your values were not new. So we laugh about this because, there's different ways to interpret this. One interpretation is that these very prominent graph theorists with hundreds of papers, thousands of citations, were amazed by our brilliance and computational ability. Maybe. Of course, a more likely explanation, a more likely interpretation is that they were amazed that anyone cared enough to compute these values. Of course, we had a good reason. We were interested in this geometry problem. We needed to know the next few values. We knew that some value less than 20 was going to be good enough. And if we plugged away, we'd figure out what it was. We were really lucky that the value was only 9 because the problem got pretty hard. But anyway, so we think that these values for 7, 8, and 9 are new. Okay. I have 2 slides left on some proof ideas. This is now, the little bit of graph theory we had to do to put into our problem. And there's some nice ideas here. Definitely going to finish a little short, but that's okay. So the first idea has to do with graph embeddings. So this is something I've been learning a lot about, and I find it a really beautiful subject. So say you have your graph and you're trying to prove that there's a small cycle. Well, one really good case is when the graph embeds in the plane. These are called planar graphs, a famous class of graphs. Okay, but now if you think of embedding in the plane as a compact set, what that means is that's equivalent to embedding in the 2-sphere. All right, so planarity, which is this good condition in graph theory, is equivalent to embedding in the 2-sphere. Well, we all know about topology, so embedding in the 2-sphere is great, but still good is embedding in the projective plane or the torus or a surface with small genus. Okay, so that's the input, is that you have a graph that embeds into a surface. And the conclusion is that the systole is small. Okay, so there's a bound on the systole. It depends on how bad the surface was. All right. And you can see, though, if you fix the surface, this grows like 1 over b. So that's really good for trying to show small systole. I'm going to illustrate an example which also shows you how to prove it in just a second. I want to first do an example. So I mentioned this hemidodecahedron and that it embeds in real projective space, the real projective plane. So if you plug in the values here, the Euler characteristic of this is 1. The Betti number of that graph was 6. And so you get 2 over 6 minus 1 plus 1. That's 1/3. That's the value I mentioned is the answer, is the optimal bound for Betti number 6. And for this graph in particular. Here's another graph. This is one of my favorite graphs now. Not that I know that many, but this is called the Haywood graph. This has 14 vertices, 21 edges, Betti number 8. And it famously embeds in the 2 torus. So here's the embedding. All right, so this is the bike path in Munster. What I've done here is label these bricks 1 through 7. And then in the row above it, I labeled the bricks 1 through 7, but with a cyclic shift. And same with below. And now you imagine extending this periodically, vertically and horizontally. All right, this gives a 2-periodic tiling of R2. You have a translation to the right by 7 bricks and a translation that's kind of up and a little, right, diagonally. If you take the quotient by that pair of translations, you get the torus, of course, and this you have these 7 faces of that embedding. Now, I can't really zoom in. I'm not sure I can do that, but if you look at the places where 2 bricks have corners that meet, so like at the top of this one here, okay, the bricks labeled 3 and 4 come together at this corner. You can think of that as a vertex of the graph. And then the grout lines coming out, there's 3 grout lines coming out. Each of those grout lines is like an edge. So this is a vertex with degree 3. There's 3 edges coming out. And you do that at each of these bricks. And altogether, each brick has 6 vertices if you count carefully. 1 at each of its 4 corners, but then 1 more like a billiards table. 1 more on each of its long sides. All right. So this is an embedding in T2. And if you look closely, the reason this graph is famous is because each of these bricks touches or shares an edge with the brick of every other number. All right. This shows that the 4-color conjecture on the torus is false, and it shows, in fact, that you need 7 or more colors. That's kind of the history of this graph, 19th century graph theory. For us, though, this was one of the graphs that came up. It's embedding number 8. This was within our realm. And the fact that it embeds in the torus tells you that you get this estimate, but I want to prove it in this case. So I mentioned that if you take away the graph, you have these 7 faces. Think of these 7 bricks. And the boundaries of each of those faces is a cycle. And so if you're minimizing over all cycles, that's smaller than minimizing over these 7 cycles. And the smallest of those 7 cycles is at most the average of those 7 cycles. All right. Now, because we've done this sum in a symmetric and beautiful way, when you add up everything, it's a nice answer. And the answer is that you get, you count each edge exactly twice. Like the edge between 5 and 6, right? That's counted exactly twice. And so you get 2 over 7 times the total weight of the graph. If I didn't say this already, this beautiful lemma is due to Mikhail Wiemeler. He came up with this, and let me just say, for anyone who actually looks at the paper, this made it a lot shorter than the first couple proofs we had. This is really, I think the lemma just by itself is beautiful. It was also extremely useful for us. Anyway, so that's basically the proof. The key thing is to figure out why it's a 7. You have to count using the Euler characteristic. You have to count how many faces there are. It's an elementary thing, though. It's really a pretty easy proof. Okay, one more example for Betty number 9. I mentioned this was a critical Betty number. Then the goal here is to show that it embeds in an Euler characteristic 0 surface, the torus or the Klein bottle. Because then if you plug those numbers in, Euler characteristic 0 means that's not there. And you have 2 over 9 minus 1. That's that magical blue fraction of 1/4. So one method to try to prove this theorem is to show that all graphs of Betty number 9 embed in the torus or the Klein bottle. Unfortunately, that's not true. So we do have to combine this with other ideas. But I do want to mention some work of a PhD student of mine who's classifying the graphs that embed in T2 or the Klein bottle up to this Betty number. It's known for abstract reasons that the total number of graphs that embed in the torus or the Klein bottle, excuse me, the total number that don't embed is a finite list if you order by subgraphs and minors and things like this. There's like a finite list of obstructions. This is a famous result going back to Roberts and Seymour. For a torus and for a Klein bottle, the list is in the hundreds for cubic graphs. But what this is exploring is for these small Betty number graphs. We have some applications in mind, in particular things like higher systoles, where you're not just looking at the shortest cycle, but the sum of the shortest k cycles. You can see here, really what this estimate is giving you is that the sum of the smallest 7 cycles is a small number, where 7 is a function of the Betty number of the graph and the Betty number of the Euler characteristic of the surface. Okay, So I mentioned that that's not enough. These sort of embedding, this embedding lemma isn't enough. So we have to combine this with something else. And what we do is we combine that embedding lemma with two things. First of all is a non-trivial result from topological graph theory. This is Glover and Hunica from 75. What they do is they consider embeddability in the projective plane. And for the case of cubic or trivalent graphs, they prove that there's exactly 6 obstructions. In other words, if you have a cubic graph that does not contain one of these as a subgraph, then it embeds. That's the theorem. It's not a particularly easy paper to follow. It's a non-trivial result. I think this paper and then subsequent papers that considered the general case by Archdeacon were important results in topological graph theory. We took them off the shelf. We were happy to assume them. But I want to emphasize that we didn't somehow reprove this. The other thing we did was prove a number of recursive estimates. We needed another 3 or 4 different estimates. And this is the sort of thing you do where you're thinking inductively. You pull out an edge, you study that graph, which is smaller. And usually when you pull out an edge, you've decreased the Betti number. So you get estimates in terms of graphs with Betti number b-1. And then, of course, like all inductive proofs, you put it back in and see what happens. So we got a number of estimates that way. And we really had to kind of kitchen sink the proof. We used a recursive estimate sometimes. We proved an embedding other times. Altogether, the proof is not that long. Our first few proofs were pretty horrendous, but I think in the end it's pretty nice. But the one thing that I'll mention is that it uses this non-trivial result. It's a beautiful result, but somehow the proof shouldn't need such a heavy hammer. And so I just want to advertise work of another student of mine who has independently calculated this S of B for these Betti numbers. And specifically, it relies more on the recursive estimates, and it does not need to cite this result from Glover Hunica, this is I think this is really nice because it provides an independent proof. And in the meantime, because she's doing this more systematically, she's getting better estimates. The estimate of S of B itself is already optimal, but she's getting lots of refinements if you filter by other graph invariants. So that's it. Here's some references. Thank you for your time.
Thank you, Lee, for a really interesting talk. Are there questions?
Very nice talk, Lee. So we just had a speaker in one of the colloquiums here who was talking on matroids. So Christopher EU, I think is this, or EUR is his last name. And so I mentioned this paper to him. He hadn't heard about it. So I sent him a copy. Maybe he had all kinds of results about matroids, just not regular ones. I don't know if there are more results in that direction that one could apply to these kind of ideas of torus representations. Maybe matroids that aren't regular.
Yeah, I'm interested in learning more. As there's certainly been people previously that found some application of matroids or some connection to matroids. But yeah, there's this whole theory. It's a big, yeah.
Also in positive curvature, you mean?
Different parts of geometry.
Okay.
Actually, Karsten had a student, Ed Schwartz, who was also with representations, I believe.
I vaguely remember him, yeah. Okay.
We've tried Googling, matroid representation, matroid, and and different combinations, and this, as far as we know, this particular link has not been found. But
okay.
Certainly, yeah. Thanks for mentioning that.
Okay, I have to go teach now. Bye, everyone.
Okay, thanks for coming.
If a graph embeds in like a 3 manifold or something, is there any analog of, you think there might be any analog of the results about embedding in surfaces or?
Can you repeat the first part? I didn't quite.
Oh, so they have this wonderful lemma about if a graph embeds in a surface, you get a bound on a systole. Can you say anything about if it bounds in some higher dimensional manifold or is that even?
Bounds. Oh, I haven't thought about that. So, so a higher, okay. I don't know. Occasionally I go to a talk in topological graph theory and I usually don't understand anything. They put graphs in all sorts of things.
And I didn't know that would be something useful or not either. I was just
Well,
curious.
yeah, I mean, I just don't know. I know so little about, anything relating to graphs and combinatorics, but definitely interested to learn more.
Really beautiful how all this comes together. Really nice.
Yeah, thank you. We had a lot of fun.
Any other questions or? If not, thank you again. And we're going to be taking a break for the end of the year. Wish everyone a wonderful new year. We'll be resuming in the middle of January.